Hi, and welcome to Week 5 Mini Lecture 1 for Thermodynamics for Educators.
In this lecture, I'm going to clarify a few points raised in the derivation of the multiplicity of the ideal gas given in the textbook. Now, the derivation in the textbook is quite me and very hand-waving, and you should skip most of the details there. There are a couple of steps that you'll find don't seem to make a lot of sense. They didn't make a lot of sense to me the first couple of times I went through it, and there is a much better way of deriving it, which we will get to towards the end of the semester. But nevertheless, there are a few basic points that are important to grasp, and I'm going to go over them now. So the problem is, how do we count the microstates of an ideal gas? What is a microstate? For a system of, say, coins, we know what the microstates are. They're fairly easy and intuitive to picture. Well, in an ideal gas, let's just take a single molecule for now and see what the microstates are of a single molecule of gas inside a container. Well, there are two types of microstates we can define. One of them are position microstates. So the molecule can be in a number of positions, the number of locations inside the box where the molecule can be. And we can just count those, and each one is a different microstate. So the molecule could be here, that's microstate 1. It could be here, that's microstate 2. It could be here, that's microstate 3. But, of course, classically, space is continuous. There are, in fact, an infinite number of places that this molecule could be in this box. So are there an infinite number of microstates? Well, no, there aren't. And the reason that there aren't comes down to quantum mechanics. Now, this is covered in much more detail in the quantum mechanics course. So again, you're going to have to take this result as given. There is a very famous result in quantum mechanics called Heisenberg's uncertainty principle that says that you can't know the position and momentum of any particle to any accuracy you want. If you know the momentum to some accuracy, then the position is only known to within some accuracy given by Planck's constant, which is a constant of nature, divided by the uncertainty with which you know the momentum of the particle. Okay, and Planck's constant is a very, very, very small number. You can look it up if you want. It's of order 10 to the minus 34. So the uncertainty in the position is very, very, very small, but it exists. And that means that essentially space can be thought of as being split up into little tiny boxes. So I've split the container of gas into lots of little boxes. Now, in reality, these boxes are phenomenally tiny and there are phenomenally many of them. But let's visualize it like this for now. So what this uncertainty principle means is that whether the particle is here in the little box or here, that's the same microstate because we can't tell the difference between these two states, according to the uncertainty principle. And therefore, the total number of positions in the box is given by the volume of the system divided by the size or the volume of one of these tiny little boxes, and the volume of one of these tiny little boxes is just given by Heisenberg's uncertainty principle. This gives you the size of, or the length of one of these boxes, and so if you cube this, then you get the volume. And I'm going to call these uncertainty boxes. So the total number of position microstates inside your computational volume here, inside the volume of the container of your gas containing one molecule, is equal to the volume of that container divided by the volume of one of these absolutely tiny uncertainty boxes. So this is proportional to the volume of the system, which is a first important result. So if you want to increase the number of microstates, you can increase the volume of your container. Okay, now that's not the only type of microstate. We can also have momentum microstates. For any position in the box, a molecule can have a great number of different momenta. Okay, so for example, if the particle is here, it could be moving in this direction or it could be moving in that direction. Right, and these are two different microstates corresponding to the same position microstate. Right, and you can keep going. Classically, there are an infinite number of directions that the momentum can point in. There are also an infinite number of magnitudes of momentum. Right, the magnitude of the momentum gives you the speed at which the particle is moving. For example, remember, momentum is just mass times velocity. Okay, so let me introduce a very important concept here. The components of the momentum is a vector, so we can split it up into x, y, and z components. And we can plot those components on x, y, and z axes. Okay, so this axis gives the x component of momentum, this axis gives the y component of momentum, and this axis gives the z component of the momentum. So this behaves like regular space, but it is called momentum space because what it actually pictures is momentum, and it's important to get used to using the space. So let me give you an example. If you have a particle like this and it is moving with a certain speed, and let's say that the y-axis is pointing upwards, okay, then this particle here is moving along the y-axis, and it has no components along the z-axis or the x-axis. So its only component is its y component, and its y component has a certain length, a certain magnitude, right? So we can depict this particular momentum as this single point here in momentum space, which says that the z and the x components are 0, but the y component has this magnitude given by its location along the y-axis of the momentum component. Okay, what happens if it has most of its components along the y-axis, but it is pointing a little bit along the z-axis as well? Well, in that case, this momentum vector here corresponds to this point here in momentum space. If it's pointing in this direction, then it corresponds to this point in momentum space, and so on. So if we don't change the length of this vector, but we alter its direction, going from the y-axis round to the z-axis, then we trace out a quarter circle in momentum space like this. And if we keep going, keeping the magnitude constant, we're just going to trace out a full circle like this in the y and z plane of momentum space. So a constant magnitude of momentum actually corresponds to the surface of a sphere in momentum space, okay, because this arrow could also point in directions which have components along the x-axis as well. We've just shown we're limited here because the screen of this computer is two-dimensional, so it's hard to depict three-dimensional vectors. Just imagine taking the circle and then rotating it around the z-axis to make a sphere. The surface of that sphere corresponds to all the possible momentum vectors that this particle can have with this magnitude. So why are we keeping the magnitude of momentum constant? Well, it's because a given macrostate of an ideal gas is defined by a certain value of the total energy U. And for a single particle, the total energy U is just equal to a half mv squared, the kinetic energy of the particle. And because momentum is mass times velocity, therefore velocity is momentum divided by mass. So substituting that into here, the kinetic energy of a particle is just momentum squared divided by 2 times the mass of the particle. The momentum squared is just equal to the square of the 3 components of momentum by Pythagoras' theorem. We can rewrite this formula up here as p squared is equal to 2mu. So in other words, if u is constant, as it is for a given macrostate, then the total magnitude p of the momentum is also constant. So on a given macrostate, for a single particle, the allowed values of momentum lie on the surface of the sphere, and the sphere has a radius in momentum space given by the square root of twice the mass of the particle times the total energy of the particle. There is still an infinite number of points on the sphere, so does that mean there are an infinite number of microstates? Well, no, because of course we have the uncertainty principle again. Remember, the uncertainty principle, if we go back a few slides, states that the momentum has a certain amount of uncertainty to it. So in fact, the sphere itself is divided up into a number of points, and anywhere between these points counts as the same microstate. And the distance between these points is given by the uncertainty principle and is still really, really, really small, which means that there are still a very, very large number of microstates around the surface of this sphere. And also the surface of the sphere itself gets smudged out by the uncertainty principle. So the uncertainty in momentum says that we don't know whether the surface of the sphere is actually over here or over here. Okay, so the surface of the sphere gets split up into, again, little chunks, and each chunk has a volume that is proportional to the total energy to the 3/2 power. Why 3/2 power? Well, the volume of each chunk is going to be proportional to the cube of momentum, since volume is the cube of whatever dimension the space is. In this case, it's momentum space, so in this case, it's the cube of the momentum. But momentum is proportional to u to the 1/2 power, so the cube of the momentum is proportional to energy to the 3/2 power. So we end up with this basic recipe here, that the number of microstates for a single molecule of gas is equal to the number of position microstates times the number of momentum microstates. The number of position microstates we saw is equal to the volume of the system divided by the volume of the uncertainty box, and that gets multiplied by the number of momentum microstates, which is equal to the volume of the shell of the momentum sphere divided by the volume of the uncertainty box in momentum space. And this number of microstates, which remember we call omega, is proportional, therefore, to the volume of the container of the gas times the energy of the gas to the 3/2 power. Okay, now this is valid for a single particle, okay, a gas made up of a single molecule. Well, that's not much of a gas. Ordinary gases have lots and lots of molecules. So if you have n molecules, this formula generalizes so that the number of microstates of a gas is equal to the volume of the container to the nth power times the mass of the particle to the 3n/2 power times the energy of the gas, the total energy of the gas to the 3n/2 power. And for macroscopic systems, for ordinary ideal gases like the gas in the room that you're in now, n is of order 10 to the 23, Avogadro's number. So, for example, if you take a container of gas and then you increase its volume twice, so you double the volume, then the number of microstates here increases by a factor of 2, that's the factor you've increased the volume here, to the power of n, where n is 10 to the 23. So that's 2 to the power of 10 to the power of 23. That's a phenomenally large number of microstates that you've just added to the system by increasing the volume. Similarly, if you increase the mass of the particle or the total energy by a factor of 2, then the number of microstates increases by a factor of 2 to the power of 3/2 times 10 to the 23. These are what are known as very large numbers, and this is what to take away from all of this. Finally, a heads up, this week we're going to be dealing with very large numbers, and one technique to get a grip on very large numbers is to take their logarithm. The logarithm of a very large number is just a large number, which is slightly easier to deal with. So we've got to get used to using natural logs and their inverse, the exponential function. We're going to discuss in the threads about natural logarithms, both the mathematics of them and how they are taught. If you need a refresher on natural logarithms, I've linked to a number of very useful videos in the week's work.